Alright guys, so today we're going to start our discussion of rates with video 2.1.1, so this is the 2.1 lesson. And the first thing we're going to do is we're going to look at this reaction. So we have N2O5 gas and it's placed in a container and it's allowed to react. So when it reacts over time, it forms NO2 gas and oxygen gas here. So you can see that according to the graph here, this is going to be our N2O5, and we're going to allow that to react, and you can tell that that concentration is going down over time because it's reacting. So we're using up some of that reactant. So we would expect the NO2 and the O2 to increase over time. So starting at 0, because we didn't start with any of it, you would expect that curve to go up over time for NO2 and also for O2. So the question is then, what do those curves look like? We can get some sort of idea by looking at the balanced stoichiometric coefficients here. We can see that there's a 2 in front of the N2O5, and we can see that, for example, the NO2 appears at twice as fast, because there's a 2 here, there's a 4 here, that's double. So just down at the bottom, right over the NO2, I'm going to write a little times 2, and we'll see why we wrote that there later to help us out. But just a times 2. And then if we take a look at the rate of the O2 gas, we can see that this is appearing at half the rate that the N2O5 is disappearing. So we have a 2 here and a 1 here, so we can see that this is half the rate, or divided by 2. Divided by 2. Okay, so to figure out what these points are here, we're going to go ahead and solve for the concentrations at various times. So here we have time 0 all the way to 100, concentration of N2O5, this is going away, and the concentration of NO2 and O2, these are both appearing. So at time 0, obviously we don't have any of our products formed at this point. So this bracket right here, this means concentration, and anytime you see brackets around anything, that means molarity. So brackets, I'm just going to write that over here, equals molar, so that's a concentration. Make sure you do remember that. Okay, so over here, let's take a look at the difference. So to find the rate, we're basically looking at the change in something, in this case the change in concentration, over the change in time. So here, to figure out our first change, what I'm going to do is I'm going to take my original 0.100 concentration of N2O5, and I'm going to subtract what we're at after 25 seconds. So minus 0.0841. Okay, so that's going to be my difference here. But remember that your NO2 is going to be appearing at twice the rate that N2O5 disappears. So I'm going to take this whole quantity and multiply that by 2. So go ahead and put that in your calculator and write the answer here. So go ahead and pause it, put it in your calculator. Okay, so you should have gotten 0.0318 for your answer. If you didn't, make sure you put parentheses around this before you multiply. Remember order of operations here. So pulling this through, going all the way down, we're going to do the same thing every time. So here, let's calculate the next one. So our next one, we're going to take our original concentration, because we're going to compare this with the original from 0 to 50 seconds now. So 0.100 is our starting concentration, minus 0.0707, which is what we're ending up at. And then we're going to multiply that again by 2, so go ahead and plug that in to your calculator. And then go ahead and do the last few too, and pause the video and do that. Okay, so you should have gotten the following numbers: 0.0586, 0.0810, 0.100. Okay, so now let's do the other side. Let's look at the O2. O2 is going to be done in exactly the same way, except for we're going to divide by 2 at the end, because that's appearing at half the rate that N2O5 is disappearing. So I'm going to take 0.100, my original concentration, subtract that from what we're at 25, so 25 seconds, 0.0841 divided by 2, plug that into your calculator. Go ahead and plug that in and get the number for here and then all the other ones as well. Okay, so your numbers should be 0.0841 0.00795, 0.0147, 0.0203, 0.0250. So make sure that you get the correct numbers. Then I would like you to take a second, pause the video, and go ahead and graph this. So I'm going to pause this as well and graph it so you don't have to watch me plotting points. You go ahead and do that as well. Okay, so you can see I've gone ahead and plotted my points here, and our results seem to make sense. So our N2O5 is decreasing over time. Our concentration is going down as it's getting used up, and it's turning into our products, O2 and NO2. And we can see that O2 appears at about half the rate, so the slope is about half as much, and then over here, NO2 is at about twice the rate, so the slope is about twice as steep as our N2O5. And that was confirmed by the math we did down here, and also is reflected in the coefficients of the chemical reaction here. Okay, so that was drawing the curves. Now, for time equals 0 to time equals 25 seconds, we're going to find the rates of these. So we're going to actually numerically calculate the average rate. And a rate is just the change in the concentration over the change in time. So our change in time for all of these is going to be 25 seconds. And we're going to look at the different rates over time. So our change in the concentration of N2O5 over the change in time. And so plugging in these numbers, my two numbers here for our N2O5, we have at 25 seconds 0.0841, and at 0 seconds our starting concentration is 0.100. So I'm going to do final minus initial here, so 0.0841 minus 0.100, and this is of course going to be, I should write molar there, molar, divided by 25 seconds because that's our change in time. And when you plug this into your calculator, you should get negative 0.00064 moles per inverse seconds, moles per second. So moles times inverse seconds, or moles per second, however you prefer to write it. And this is a negative. That negative is a really important symbol here because that's telling you that the N2O5 is decreasing in concentration over time by this much molar per second. Okay, so let's do the next one, NO2. So the change in NO2 over change in time. I want you guys to go ahead and pause the video, finish NO2, and then also try O2 on your own and see what you get. Okay, so for our NO2, our final over here, NO2, is going to be 0.0318 minus 0, in this case, that's what we started with, molar, over again 25 seconds, and that's going to give us a positive number. Positive because we're forming this NO2 over time. So positive 0.0013 molar per second. And then we're going to do the same thing with O2. So the change in the O2 concentration over the change in time, and that's going to give us we're going to use these numbers here, 0.00795 minus 0 molar over 25 seconds. And plugging this in, you also get a positive number because you're also forming oxygen, 0.00032 molar per second. Okay, so those are your concentrations. And again, really important, don't forget these signs. Negative means it's going away or getting used up, so it's a reactant. And positive means products because these guys are getting produced or made. Okay, so how did you find the rate using the graph? So if you had your graph, in order to find the rate, the only thing you'd have to do is take the slope of the tangent line. So the rate at this point here, at say 50 seconds, is whatever the slope is of this tangent line. So you'd have to find that slope. The rate of O2 formation at the same time would be the slope of this tangent line right here, etc. So you can see that the steeper the line, the faster the rate. And the less steep the line, the slower it's going. So rate is going to be equal to the slope of the tangent line at that time. The concentration data we can also use to find the rate, and that's what we just did up here. We just used the change in the concentration over the change in time. So the rate equals change in concentration over time. And so that formula, change in the concentration of X, whatever X is, whatever substance that is, over the change in time. Now, using the tangent line, this is often called the instantaneous rate because you can see exactly what the rate is at any one given point here. And then using concentration data, that's more of an average rate because we're looking at the rate change not at any one instantaneous point here or here, but the rate change over this whole section of time. How does the rate of NO2 compare to that of N2O5? So we kind of already answered that before. The rate of NO2 is twice that of N2O5. That's how we got these numbers here, based on the balanced equation. And that's also confirmed by the rate calculations. You can see that those rates, they're exactly the same as we predicted. So the rate of NO2 formation is 2 times that of N2O5. Based on the balanced equation. This is confirmed by the rate calculations. Alright guys, that is the end of video 2.1.1.